undergraduate studies, Amran authored 11 publications in the field of carbon nanotubes, which have collectively garnered over 1,100 citations. As part of his research, PhD research, Amran also worked at the National Institute of Standards and Technology in Boulder, Colorado, and at the Israeli Institute of Technology in Haifa, Israel. Since obtaining his PhD, Amran founded Wootz, along with two co-founders, to bring advanced carbon nanotube materials to market through repeatable and scalable technology. Welcome.
Thank you very much. And thank you all so much for this great opportunity, for hosting me down here at the Rio Grande Valley Angel Network. Really appreciate it. I'm Amran, CEO and founder of Wootz, and we are commercializing high-performance materials made from aligned carbon nanotubes, which throughout the presentation, just to keep it short, we call CNTs. So our product is a truly multifunctional material with a very unique combination of high-performance properties. This material is stronger than steel, half as lightweight as aluminum, is as flexible as sewing thread, it's biocompatible with human body, and stable in even the most chemically aggressive environments. It's an exceptional conductor of heat, besting even metallic heat sinks, and it's electrically conductive, surpassing other fibers, textiles, and polymers. You can basically think of this as sort of electrically conducting super nylon. Now, with the rapidly accelerating trend of digitalization in our society, several applications have started to emerge where electrical conductivity is no longer the only requirement for material of construction. For example, if you want to make a flexible display, you need an electrode that is flexible, durable, optically transparent, and electrically conductive. Overhead transmission lines now need to carry more power than ever before, more reliably than ever. So, if carbon nanotubes can truly do all of these amazing things, what's the story here? Where do they come from, and why don't we see them everywhere already? So the first company that tried to commercialize carbon nanotube yarns and fibers was called Nanocomp. They got the first bite of the apple back in 2004. But their approach was to use a solid state process. And this was a lot like spinning cotton yarn from raw, fluffy cotton. It did not lead to high performance properties. If you've ever worked in the plastics industry, you know that you get the best results by processing molecules in a fluid state. That's how you get the most bang for your buck. Fibers like Kevlar, nylon, Xylon, Dyneema, Spectra, even the precursor to carbon fiber, all of these materials are processed from a fluid state. And this is what Dexmat, our other competitor, went after in 2015. However, the properties of their material come with enormous uncertainties and at a very prohibitive price point. Just by way of example, a single meter of their 1 millimeter diameter braided CNT fiber costs $1,000. So 7 years in, it's not really a surprise that they've not broken into any mainstream markets yet. At Wootz, we've designed our own fluid phase process in order to more reliably and scalably capture the potential of this amazing molecule. So how does it work? We first buy raw carbon nanotubes from suppliers in order to lower our costs, and use an in-house purification process in order for them to be usable in the fluid state. Our novel cryogenic blending approach allows us to mix a stable carbon nanotube fluid in minutes instead of hours, and continuously rather than batch-wise. We can then work with a low concentration fluid, or ink, that can be sprayed onto a substrate in order to provide a carbon nanotube coating, or we can mix the carbon nanotube fluid at a higher concentration and run it through an extruder, which then produces hundreds of little thin fluid filaments that are later drawn and solidified into an aligned carbon nanotube fiber. So the key takeaways here from the process are, first, no other competitors have a continuous fluid phase process that is designed for scale-up. Similar versions or iterations of our process apply equally well to produce coatings, films, and fiber products, and similar versions of these products apply to a very broad range of markets and industries. So if we gain traction in our early beachhead markets, this will serve to significantly de-risk our long-term commercial vision for this material. This is how we operate as a business. We do not make carbon nanotubes. We buy carbon nanotubes from suppliers, and our in-house purification makes them usable. But more importantly, we can be versatile and work with different compositions and blends of carbon nanotubes to fine-tune the properties of our product for a given customer or target application. We then sell these carbon nanotube films and fibers for a customer to augment an existing product line, or just wholesale to a distributor, depending on the industry that we're in. As part of our service-based model, our partner can send us their material, and we apply our carbon nanotube fluid to deposit a carbon nanotube film as a coating on their material. We can also modify our carbon nanotubes in order to facilitate their integration into a functional composite. Ultimately, however, we're B2B. The final device integration falls on our customer. So how is this cool new technology going to lead to our first revenue? The most significant recent development at Wootz has been our partnership with Kureha. Now, Kureha Corporation is a large publicly traded Japanese materials company that specializes in high-performance polymers. And after doing some due diligence in our data room, they decided to commit to be the lead investor in our seed round. However, separately from their investment, we've also executed an MOU, which will serve as the basis for a joint development agreement to develop and commercialize 2 specific applications for our technology. I'll talk about these now. The most technologically mature application is flexible displays for touchscreens. So everyone here who has a cell phone in the room, if you've ever cracked your screen before, it's because the screen is made of ITO, indium tin oxide. It is a very brittle material. Now, just to be clear, we're not seeking to replace ITO. We can't be cost competitive yet. We're going after a TAM where ITO simply cannot compete, namely in flexible displays. ITO cannot be bent. So our approach here is we're going to coat the carbon nanotube fluid on the piezoelectric material provided to us by Kureha. Now, what does this word mean, piezoelectric? It means that this material actually generates an electric charge when it's deformed. So it doesn't need an external power source like a capacitive touchscreen does. Kureha is already active in this space. In fact, they've already led the Series B for Cambridge Touch Technologies, which is a startup based in the UK that's innovating on the signal analysis and software backend for these new types of displays. Now, they anticipate up to 5% market penetration by 2025, and at the price point they're willing to pay for this coating service, this will roughly correspond to $20 million in gross revenue for Wootz. Because of the size of this opportunity, though, if we're successful here, both parties, under the MOU and the JDA that will follow, anticipate entering into a joint venture to rapidly grow our market share. The second application is in oceanic energy harvesting. Now, I know this probably looks and sounds wildly different from the one I just mentioned, until you remember that a piezoelectric material generates electricity when deformed mechanically. So in the past, this industry has really been hamstrung by the nature of the oceanic environment. Nobody questions that there's a lot of energy in the world's oceans, but that also works against you if you're trying to build a structure out of durable, permanent materials that's supposed to withstand everything from a slight gale to a full-blown storm. Here, we're bringing to market a carbon nanotube coating that will serve to harvest the electric energy from the surface of their piezoelectric material. Carbon nanotubes are light, flexible, and extremely durable, but more importantly, they do not corrode in seawater. Now, Kureha has done a theoretical estimate, and they anticipate that a 10-layer structure of alternating carbon nanotube electrodes and PVDF, their piezoelectric polymer film, could generate up to 1,000 watts per square meter. That's 6.5 times more than solar. It's a purely theoretical estimate, to be sure, but even if they're off by, say, a factor of 5, this is an energy source that is constant throughout the day. So even so, the potential upside here could be really massive. The best thing for us, I forgot to mention, is we're still doing the same thing as in the first application. We're coating our carbon nanotube fluid on the same PVDF material that they're providing us with. So right now we are raising a $2 million seed round through convertible notes. We're 75% subscribed and our lead investor is committed. We have still $500,000 in headroom available in our round. Obviously, the timing for the Series A and Series B rounds are going to be linked to some of our technical and commercial milestones, but in the near future, we do anticipate closing our Series A by the end of Q1 of 2023. Primarily, this $2 million raise is so that we can outfit our pilot plant with the required manufacturing equipment to produce carbon nanotube materials at a commercially viable scale. Previously, we raised a little over $600,000 from founders, friends, and family, and this has allowed us to build our own facility from the ground up. Today, it features a workshop, a chemistry wet lab, some office space, and a heavily modified high cube shipping container, which will house the future pilot facility, pilot production line. I think I'm nearing the end of time, but just want to say we really have a great team together, core expertise in carbon nanotube material science, manufacturing engineering, extrusion technician. We've recently onboarded a new COO who was our general counsel at Vincent & Elkins. Extremely grateful to have her on board. And I'd like to hit on our partnership with Fluor. They're a large EPC firm, engineering, procurement, and construction, and we've partnered with their business incubation group, so it's not just 3 guys in a shipping container in the middle of Texas doing this. They are making sure that we're very reasonable with our scale-up targets, and that we don't go down any sort of like dead ends from an industrial manufacturing standpoint. So with that said, I'd like to turn it over to questions. I hope, yes?
When do you think you'll be profitable?
We anticipate being profitable by 2023. So our JDA with Kureha makes, there's room in the budget there for our consulting services. So even while we're in the research and development phase of our agreement, they're going to pay us for our time, for our materials, and equipment costs as well.
What's your exit look like, or what are companies in your lane exiting at?
Companies, there's not a whole lot of comparables because there's like just those 2 prior competitors that I mentioned that tried to commercialize carbon nanotube materials. But if I had to point to an exit, it would be the likes of a 3M or DuPont or Honeywell.
So the biggest players right now in that 12.3 billion are 3M, and who else did you mention?
Well, Honeywell. But they're materials companies, right? And so it's not necessarily that they're extremely active in those beachhead markets. That's where we're focusing on right now because of our partnership with Kureha, and that's where really there's a lot of potential. There are a lot of other applications once you're more scaled up that you can contemplate. So I mentioned like overhead transmission lines, that's like one of the more forward.
Who do you buy the nanotubes from?
We've got about a dozen different suppliers that we like to work with, but the carbon nanotube industry has grown by leaps and bounds over the last decade. There are a little over 100 suppliers out there. The total market size is $5.2 billion for nanotubes worldwide. It's now thousands of metric tons of production capacity, but nearly 80% of that global market is not making an all CNT material. It's using carbon nanotubes as an additive in plastics. So you add like say 2 4-weight% carbon nanotubes to a polymer master batch, suddenly it's electrostatic dissipative, it's more thermally conducting, more UV resistant. That's where the market for nanotubes is today.
Are most of those domestic, or are they somewhere else in the world?
It's pretty spread out. Asia kind of has a lead.
Biggest.
Yeah, but North America is second.
Any risk that you see there because of that, potentially?
Well, who knows what the world will look like, right? But it's a very good question.
Something to entertain right now.
Yeah, we stay away from Chinese suppliers, and early on we were working with a company that is actually, we found out later, is owned by Wootz Nano, which is part of a Russian conglomerate. And I'm counting my blessing that we actually are not, we didn't develop any of our process around those nanotubes.
So currently, I know that Samsung and a couple of the Korean companies have the, displays, folding displays and all that. Are they using that same type of technology, or how is that different? How's yours different from theirs?
Those are still capacitive touchscreens that use ITO. Where they've innovated is in terms of really, really pushing the limits of what the ITO can bear. But they're still capacitive. So those foldable displays, a lot of times you can only fold them along a specific fold line, right? And that's where they basically try to push the limit. This is something that, I'm not going to come out with so much confidence as to say it's like a yoga mat that you can work out on, but that's more the ballpark. So it's closer, our application is closer to that than it is to the flexible display Samsung is well.
And then what's your I don't want to say secret, or what's your IP per se, to being able to transform nanotubes over to this?
Yeah, so I actually did forget to mention, our process patent was granted by the USPTO in September. And our IP attorneys at Foley and Lardner are very confident that this indicates it will likely also be granted in the 7 other jurisdictions that's currently pending in. So the most innovative parts of the IP are the cryogenic blending, because preparing a carbon nanotube fluid right now on a lab scale, you need centrifuges, you need sometimes like a variety of very complicated mixing equipment. We do the mixing at a cryogenic temperature, which allows us to basically pre-mix the solvent in an unactivated form with the carbon nanotube material. Otherwise, when you just dunk it into the solvent at room temperature, it does like what flour does when you add it to water. It forms a clump with a gel layer on the outside, and you've got dry flour on the inside that you're gonna have to break up.
I'm
Yes.
totally out of my element here. About pre-COVID, I went to the CES show, I guess, in Vegas, the Consumer Electronics Show, whatever it's called, and I forget who the manufacturer was, but they had a huge display of these really cool flexible displays. Do you know what that technology might have been? Is there a similarity of what you're doing here, or is that something totally different?
If it was something that you could actually like bend like that, it's
Yeah.
possible it was a piezoelectric. However, they were not using carbon nanotubes. That's just based on sort of like the IP survey. Some of those displays will use other piezoelectric polymers. I will say though about our partner Kureha, they make the world's most piezoelectric plastic. The PVDF that they make has, so what you need is a very high beta crystalline content. They make the PVDF with the world's highest beta crystalline content. Our Kima is a close second competitor.
Can you disclose how much of your 2 million they committed to? You know?
During due diligence, perhaps. I haven't been authorized to like say that just publicly.
And when you said is it MOU? I forget the acronym, but what exactly does that entail? I'm not really familiar with that.
Memorandum of Understanding. We're basically using it as an intermediate step, which is technically not legally binding, but we've outlined all of both parties' expectations with regards to things like developed IP. So what we're going to have, that was actually the part that we did the most work on, right? Because we're talking about partnering with someone that is also a materials company, so we have to be careful. Obviously, no party gets rights to the other party's background IP that they had prior to the partnership. And we're going to try and stay away from jointly owned IP, because that really ties you at the hip for the duration of the patent. Instead, what we're going to do is the jointly developed IP will be allocated to each party based on technology category. So if they have IP, say, on the device side, even if it requires nanotubes, it's the device. That's theirs. If we develop IP on the composition of matter of the coating, say if we add some other nanoparticles in there, or we innovate on the coating process, that will be our IP.
What's your vision for the company? To grow and be the CNT equivalent of Dow Chemical, or to sell to something like a Japanese country?
Like Dow Chemical.
Dow Chemical.
No, I think realistically, the exit will probably be, if we're wildly successful in IPO, but more realistically, it'll be an acquisition by a Dow, 3M, or DuPont, or Honeywell.
5 years?
In terms of the, sorry,
5 years, 3 years, what do you think?
5 to 7 years.
5 to 7.
Yeah, our one of the applications that we're really excited about for our long-term commercial vision is in overhead transmission lines. And so on this, we're working with EPRI, the Electrical Power Research Institute. This is much further out, in the future. We'll have to be able to make tens and tens of kilometers of carbon nanotube fiber continuously at an affordable price point. But one of the big issues with transmission lines is thermal sag. So you expect to run a lot of current through this metal structure. Metals expand when they get hot. And so now suddenly your overhead transmission line is coming close to ground. It can arc to ground and spark a wildfire. And that's what happened with the Camp Wildfire in California. Some of the recent industry approach in what they're called HTLS, high temperature, low sag conductors, is best exemplified by what 3M is doing with their ACCR cable. They basically took away the steel core, which previously is used in current, old school cables, just as a thermomechanical support, and instead use aluminum conductors that are reinforced with a ceramic fiber. So the ceramic fiber is there to give the sag resistance properties. But ceramic fibers don't conduct electricity. So when they're loading their aluminum wires with this, they're actually making the cable lossier. It's safer and it has a higher ampacity, but you lose more in terms of like joule losses upon heating. So with our carbon nanotube fiber, what we're proposing to EPRI is you can have the sag resistance without the compromise. Electrical conductivity and thermomechanical.
How far are you from this? I don't have much of a science background, but I am somewhat familiar with the armchair quantum wire project that was happening at Rice.
Absolutely.
Smalley and all that, yeah.
Mhm.
So how far are you from that? 'Cause that was kind of the holy grail.
It is, yes. And it's not, we're very far from the armchair quantum wire. That requires, this whole presentation I've been talking about carbon nanotubes in general. Not all carbon nanotubes are created equal. The armchair quantum wire is basically what would happen if you were able to reliably separate out one of the 45 different kinds of carbon nanotubes that are there and make a fiber only out of that type of nanotube. We buy nanotubes from a supplier. There's 10, 20 different types in there. And we're not attacking the monster that is type-specific separation. In terms of treating it like a high-performance polymer that we can make scalably and still has really good properties, we're right now sending samples to EPRI that are up to 4 foot long for their tests. But we anticipate that with the completion of our pilot facility, we'll be able to make 1.5 kilometer long, up to 1.5 kilometer long CNT fiber continuously. So, and we need about 1 kilometer for the next level of field test. There's a big jump there.
We'll take 2 more questions.
Couple simple questions. Number one, just can you share how you got involved in this, number one, and then number two, for such a seemingly technical industry, how did you come up with the name?
Wootz. Okay, I'm so glad you asked that question. I'll get to that in a bit. A lot of my research at Rice focused on carbon nanotube materials and carbon nanotube fluids. The group that I worked in is the same group out of which DexMat spun out of. I worked with those same graduate students. We worked side by side in the research group. They went and started DexMat, and you know, DexMat didn't really go anywhere. I had a lot of conversations with them about maybe things that could be done differently. Ultimately, there were a lot of differences of opinion on the process, on the team composition, right? I didn't think that, because we have a PhD in chemical engineering doesn't make us engineers. We're research scientists. We work in a lab. And so there were a lot of different things that just didn't pan out. So I went out there with 2 other co-founders. We filed our own patent almost a year after I left Rice, after just doing, back to the drawing board. How do we mix this well? How do we align it in a way that doesn't cost an arm and a leg? That's how it came about. As for the name Wootz, who here is familiar with Damascus steel? Damascus steel.
I've heard.
Yeah. So Wootz, Damascus steel.
Oh,
It's like serious.
Yeah. It's got the really.
Shotgun barrels used to be made out of all the time.
I did not know that.
You can incorporate that into your logo.
A shotgun barrel next to
Yeah.
that. Wootz is the precursor to Damascus steel. There it is. Mistranslated by the British when they discovered it in India. It originates from the Indian steel wuku, which was the first fluid phase processed steel with a high carbon content in the old world. And it took, I believe, Damascus steel was developed during the time of the Islamic Caliphate in Europe. It took them centuries before they were able to replicate the kind of properties that those smiths back in what is today Sri Lanka were able to do with, people today, it's like the pyramids. People today are still, metallurgists today are still trying to figure out what tools did they have at their disposal that allowed them to actually make a steel like this. So it's the fluid state process and the high carbon content. That's the link.
That's what we're thinking. Yeah. We just
Yeah. This is what happens when founders kind of, nerd out over materials.
Another quick question. Do you see that may get into the residential for green energy to replace the solar or windmill type of things that people can put on their rooftop to create energy and electricity for their home household?
Well, the electricity generation part of our market is done through mechanical deformation. So, obviously, there is some potential for that to work with wind, but not nearly as much. Really, ocean energy, I mean, the energy density of moving waves is 60 times higher than wind going at the same speed. So, that's really where we're focused.
Thank you very much.
Thank you.